SwayamPrabha. Digital India. Educated India.
Hello, welcome back. Today we are going to go into the fourth lecture of this series. So, we will start lecture number 4. Okay. So far we have built up little bit of background, which is most often the recapitulation of what you already know from your schooling days. Okay. But we need to look at them more critically now, because we are going to use those information and knowledge into actually calculating few things. So, please give your attention and try to visualize all those things that we are discussing in the class. Okay. So, last time we were looking at the relationship between the sun, earth, the observer and the center of the earth. Okay. So, the critical information that we need is the apparent motion of the sun with respect to, I am just abbreviating it with WRT, with respect to the observer. Okay. Observer. So, that is the critical information, because observer is the point where we are going to place our solar energy conversion device, whether it is a photovoltaic panel, whether it is a reflector, whether it is a concentrator. So, that is the point where we are going to put our conversion device. So, the apparent motion of the sun with respect to that point is critical. Okay. Now, to generalize this thing, the observer location we need a universal reference frame, right? And in the last class we have seen that universal reference frame for us is the center of the earth. Okay. So, this universal reference frame is the center of the earth. So, with respect to that, we have seen that to connect observer position to the origin, which is the center of the earth, we needed two angles. Okay. Two angles, because it is a 3-dimensional frame. So, you need at least two independent variables. So, two angles we needed, one was latitude and the other one was longitude, right. This we have seen, and we have seen what do they mean, how to measure it and all those things. Now, the other component of this puzzle is the connection between the sun rays and the center of the earth. Okay. So, here we have seen that again we will be having two angles, okay, which will connect observer, sun rays and everything to the center of the earth. So, those two angles were, one was the declination angle, okay, which is often designated with delta, okay. And we have seen what it means. It means that the angle that the sun ray which is perpendicular to the surface of the earth okay. The angle that the sun ray which is perpendicular to the surface of the earth makes with the equatorial plane. That is the declination angle. So, it does not depend on where the observer is, it just depends on what is the relative position of the sun with respect to the earth. Okay. So, that is a very critical angle that we are going to look into detail today. Okay. The other point that we discussed, which connects to the observer to the center of the earth. In the same figure we have shown you the angle that is the latitude, okay, and that figure was this one. Okay. Here you can see that this is the normal ray that is coming and the angle it is making is called the declination angle, okay. And the other angle that we have seen in the same figure, that is the latitude, okay. This is the latitude that we have seen. Now, we are going to talk more about the declination angle, okay, because that is a very critical piece of information. So, let me draw this figure again, a little bit simplified version of it. So, let us say that we have the axis like this and this is the center of the earth. We have the equatorial plane like this, okay. And suppose the sun rays are coming from this direction, okay. So, the one that is actually radiating perpendicular to the surface of the earth, that is actually connecting to the center of the earth, which is this one, and what angle it makes, that is our declination angle, right. Let me use a different color to highlight this. So, this is our declination angle. Now, if we think of it in terms of the earth position in its orbit, then let me go to the next page. So, we have seen that if this is our orbit of the earth and if here is our sun, actually sun should be here, yeah, in one of the foci, and the position of earth, or rather the position of the axis of the rotation of earth, it changes, right. The angle between the axis and the orbital plane stays the same, it is approximately 23.5 degrees, but for any particular time of the year you have different declination angle, right, because here you can see, let us say two extremes. So, here we have seen that if this is our if this is the equatorial plane which will be perpendicular to the axis, okay, then we have seen on 21st June the sun rays will come normal to this particular plane which is the Tropic of Cancer, and on the other hand if it is 31st December, I am sorry, it is 21st December, then the normal point would lie here, that is the Tropic of Capricorn. Okay. And for these equinoxes we will have that the rays are actually falling directly onto this equatorial plane. So, for both the equinoxes, the sun rays are perpendicular to the equatorial line itself. Okay. So, from this picture what you can understand that this declination angle, it first it changes with the time of the year, okay, and on equinoxes sun radiates normally on the equatorial line, right. So, that means the declination angle will be 0 because it is the angle of the sun ray with the equatorial plane, and if it is normally radiating on that plane then the angle will be 0. So, delta will be 0 at the equinoxes, right, for both vernal and autumnal equinoxes. Now, on the other hand, on the summer solstice, again I should remind you that whenever we call about summer, we talk about the northern hemisphere summer. Okay. So, this is, so later in the course I will not repeat this northern hemisphere. So, for the first time let me talk few times so that you get the sense. Northern hemisphere summer. Okay. Now, for summer solstice the sun radiates normally on the Tropic of Cancer, right, Tropic of Cancer, which lies at 23.5, again approximately north. The latitude of the Tropic of Cancer is 23.5 degrees north. Okay. So, what do you expect the declination angle? What would it be on this summer solstice? That would be plus 23.5, right. So, this is the declination angle will be 23.5 degrees, and the convention is north we call positive. So, that is how this is positive 23.5 degrees. Okay. And in case of winter solstice we have the sun is radiating in the southern hemisphere, and that is on the Tropic of Capricorn. Okay. So, that means delta will be negative of 23.5 degrees, because if we call north positive, south will be negative. Okay. So, that is how the declination angle will change throughout the year. Okay. So, this we get just from the intuitive picture that we obtained from the definition of declination angle and the earth revolution around the sun. Okay. So, one major thing I want you to note, that declination angle does not depend on the observer position, does not depend on the observer position. This is a critical piece of information, because from now onwards we are going to use many angles, and it is somewhat confusing sometimes that which angle depends on what. Some angle depends on the apparent movement of the sun and some angle depends on the observer position. Okay. So, now if we want to quantify the variation of declination angle. Okay. So, this is a fixed thing, right? We do not have to, I mean, it is not dependent on observer position or the weather or anything else. It just depends on the earth revolution around the sun, and which is standard thing. So, we can actually find out this and we can write an exact equation for this case. So, declination angle is expressed as, let me first write and then I will explain each term. Okay. So, this is how declination angle changes. So, you can see that it has a variable portion which is sinusoidal variation, and this is the prefactor, and of course, this whole thing is expressed in degrees, in degree. If you express it in radian, the expression will change. Okay. And so, you have a prefactor and you have a sinusoidally variating part. Now, we can say that this sine function, it can either sine of whatever, it will be between plus and minus 1, right. So, you can see directly that delta will be between plus 23.45 degrees and minus 23.45 degrees, and I should use equality as well, because sine can be minus 1 and 1 as well, and here also the declination angle can be positive 23.45 degrees or negative 23.45 degrees. This we can see directly from the expression. Now, what does it mean? So, first of all, the correction that we were so far talking about 23.5 degrees. So, that is a approximation, right, or simplification. So, the actual value is 23.45 degrees, and what this positive 23.45 means? This means the Tropic of Cancer. This is the limit of the sun rays radiating normally if you go away from the equator towards the north pole. So, this is the limit of latitude in northern hemisphere till the sun radiates normally. Okay. And that is why we call it Tropic of Cancer. So, that is the upper limit, and the opposite thing is the Tropic of Capricorn. Okay. And that is exactly towards south. That is the limit the sun can radiate normally, and beyond that sun cannot radiate normally. Okay. So, that is the variation or the limits of the declination angle. Now, in the expression we have, let me rewrite this expression again, so that we can talk about the other portions. Okay. So, we have looked at the limit. Now, if we look at this sinusoidally variable portion. So, again whatever is within the parenthesis, again it is in degrees. Okay. You can see this from the quantity 360, that is the limit of a revolution, right, 360 degrees. Okay. And what is the other part? This n again is the number of day in a year. This we have seen earlier, right, n we have seen. Now, so again just to repeat, n equal to 1 on January 1. Okay. And if you are n equal to 31 plus 10, 41, that is on February 10, and so on. So, for 365 days we have 365 values of n, and depending on which day you are trying to calculate the declination angle, you will put that particular value here for n. Okay. And that is how you get this variability. Now, if we look at the variability of delta, what we get, let us try to plot it. Okay. So, let us say that in this axis we are plotting delta, and in this axis we are plotting the time of the year. Okay. So, first of all we know that it will be bounded by two limits. One is positive 23.45 degrees and the other one is negative 23.45 degrees. So, these two boundaries will limit the variation of declination angle. Okay. And we will have 2 0 points for this plot, because we have two equinoxes, and equinoxes mean the delta will be 0. So, these are two equinoxes. Now, delta will be maximum, that is positive 23.45 degrees in case of summer solstice, right. So, let us say we will have here the summer solstice. Okay. And winter solstice will be in December. So, let us say we have December here, 21st December, and then our declination angle will be the minimum. Okay. So, this is winter solstice, declination angle will be negative 23.45, and let me increase this axis a little bit. Okay. So, again, and for any other yearly variations, the variation of declination angle will also be periodic, where whenever it starts from, it has to come back again at the end of the year. Okay. So, we can draw this variation of the declination angle. So, here what we see? Here what we see that this point and this point has to have the same value. Okay. So, variation of delta will be periodic. Okay. It has to come back to the same point at the end of the year, and we have this sinusoidal variation that we can see. And so, if this is summer solstice, this will be between summer and winter, we have autumnal solstice, sorry, equinox, and on the other direction between the winter and the summer, we have the spring, or which is sometimes called vernal, just the adjective form for spring, equinox. Okay. So, this is very interesting, the declination, which actually is the major factor which tells us about the weather, and this whole declination variation is coming due to the fact that the axis of the rotation of the earth is inclined by a certain angle to the orbital plane of revolution. Okay. Nothing else, it does not depend where the observer is, where you are standing and looking at the sun, it does not depend on that, it just depend on which day of the year you are talking about. Okay. And unless this is, unless we had this variation of delta, we did not have seasons, and probably we could not have life on the face of earth. So, no life would have been possible. Okay. So, this is the very important variation that we obtained, which is behind the life on earth. Okay. Now, let me insert few pages. Okay. Now, we will talk about the next topic, which will be the calculation of time. So, we have talked about the variation of declination angle which changes with the day of the year. Okay. Now, in a day, how the time varies. Okay. That is what we are going to look at now. Okay. So, before, so now I have this watch on my hand, right, and you also have it. You have in your computer screen, you have the timer, everywhere we have time. But before that, when all these electronic things were not there, people also followed the time of day or the diurnal time. how did people do that? They looked at the sun, right? So, they were familiar with solar time. So, with respect to the position of the sun, you can find what hour of the day. Okay. So, that is what people did, and what were the fixed point for those solar time? First one was, the most important one is the noon. How people find when is noon? Noon is defined when the sun is at the zenith position or overhead, zenith or overhead position. Okay. So, I mean, for a particular day, you will see that sun starts from the horizon in the east and goes up in the sky, right, and then goes down again in the towards the horizon. That is how sun moves apparently. So, the highest position of the sun in the sky for a particular day defines the noon. So, basically this is the highest position of the sun. That is how noon is defined, and again if you talk about it, we should specify it to be solar noon. That is one fixed point. The other fixed point is the sunrise and sunset, the set of fixed point, the sun set. Okay. How do we define that? Sunrise is when the sun is at the eastern horizon, right, eastern horizon. And sunset, what do we say? When it is at the western horizon, right. That is how we define. You do not need a watch or anything, you just see the sun, you can say this is the sunrise point, this is the sunset point, and this is the noon point. This you can define, and that is actually called solar time. Okay. And this people have understood very meticulously, particularly in India. If you have visited these sun dials, okay, very elaborate sun dials are there in the Jantar Mantar. I guess lot of you have visited it. If not, you should, because then you can appreciate, before there was watch, how people could very accurately could find out time. And Jantar Mantar you can find it in Delhi and Jaipur. Okay. And actually there are total 5 of them. Okay. So, this Maharaj Jai Singh, he actually built these things. So, total 5 of them, and only 2 are alive today, other 3 are destroyed presently, and they were made like 300 years ago, within this time period. Okay. So, that is very interesting, and I think as kid you all have placed some stick on the ground and you have looked at how shadow moves for that stick, right, and that also gives you a very preliminary form of a sundial from which you can find out the time of a day. And if you have not done that as a kid, in this course at least you should go back and do that very basic experiment, okay, and you will enjoy it, I can say. Okay. Now the critical portion is, okay, we have the solar time, which is we do not need a watch for that, but ultimately the world runs on certain times, right. Your watch and my watch has to give the same time, then only we can fix a meeting, we can, the trains can run, right. We have to have some basis for standard time. Okay. So next thing we need to know is standard time. So we cannot carry these sundials, and the sundials will give you different time at different places, right, because sun rises at different time at different places. So we need some standardization, that is what we need, the standard time. So solar time varies from place to place, right. So we need some standard to fix this variability, right, and that is what we do call the standard time, and that is what your watch is showing you right now. So now what would be the connection? We need to connect these two dots, right, the standard time which your watch is showing and the solar time, okay, and that connection is given through this equation. So solar time is standard time plus minus 4 LST minus LOC plus E, okay, that is the equation that connects solar time and standard time, and what are all these terms will come one by one. Okay. So solar time is what your sundial is giving, what sundial shows, right, and standard time is actually what your watch shows, okay, and how are they connected with these other things, but your watch, so if you are in Bombay, your watch and my watch, I am at Kanpur, both of them, if they are correct, are giving the same value. How is that possible? Okay. So that is why we, for uniformity, we fix a location for which, or we fix a location in a time zone, okay, we call it time zone for the area which will have to follow the same time, okay. So for us the whole India is the time zone and we call it Indian Standard Time or IST, okay. So for this time zone we have a fixed location, the solar time for which serves as the standard time. So your watch does not know whether sun is up or not, whatever it, whenever you fix it, it follows the same algorithm and runs at a constant speed, and that is how whenever you fix it to the standard time, then it will follow, it will give you the standard time always. Okay. Now, what is this plus minus 4 LST minus LLOC part? Okay. What is this? First of all, I would say that this LST stands for the latitude, sorry, not latitude, longitude of the standard location. Okay. So, for India, for Indian Standard Time, we have fixed this location to the standard location to be the Prayagraj or Allahabad. Okay. This we fixed because it lies almost in between the east and west boundaries of the country. That is why we fixed our standard time location to be at Allahabad. Okay. And all the watches in India, they will follow the solar time of this location. That is a convenient agreement that we did between ourselves. Okay. Now, this LST is the longitude of this particular standard location, which is Allahabad for our case. And what is LOC? This is the longitude of the location of the observer. Okay. So, if you are at Guwahati, that would be your longitude of Guwahati will be your LLOC. Okay. And how come this factor 4 is coming? 4 is actually coming from the fact that the sun traverses 1 degree in 4 minutes. Okay, because it traverses 360 degree in 24 hours. So, if you compute that, you will get it traverses 1 degree in 4 minutes. Okay. That is why that factor 4 is coming, and you can say that all this time that we are writing time in minutes. Okay. So, solar time. So, if we go back to the equation here, in this equation the solar time and standard time, the difference will be coming in minutes. That is why we are using this factor 4. And there is one more thing here. Okay, yeah, this plus minus. Okay, this plus minus is coming whether the observer location is towards east of the standard location or west. Okay. So, that is the convention, or rather the fact is positive stands for when observer is located towards east. Okay. This you can understand very easily, like the sun rises in the east, right. So, if you think of Patna, which is towards east of Allahabad, right. So, sun rises there first. Okay. So, the time will be, the solar time will be higher in Patna compared to Allahabad, but you are adjusting your clock so that it shows the same time. Okay. So, that is why this sign convention is coming. Okay. Now, another factor, so let me write this equation once again. So, solar time equal to, or rather solar time equal to standard time plus minus 4 LST minus L LOC plus E. Okay. Now, we have not talked about this E. E is called equation of time, which is nothing but a correction factor that we need to add to this equation. So, this is a correction factor which incorporates the variation in day length. Okay. Because our days or the time it takes to rotate the earth around its axis is not exactly 24 hours. Okay. So, the day length is not exactly 24 hours, hence the correction is required. Okay. And the correction is done through the form of this equation of time. Okay. So, now what is that correction? So, equation of time is 9.87 sine of 2b minus 7.53 cos of b minus 1.5 sin b. Okay. And this is in, so this b, this is computed through this equation. Okay. So, again this b in degrees and b is a function of n. Okay. N is again the number of day in a year. So, January 1 is n equal to 1. Okay. So, if we look at the variation of it, okay, let us say this equation E in minute and this is month. Okay. And so, let me write few of these. Zero, 5, 10, 15 and so on. Okay. So, it varies somewhat like this. Okay. And again, like any other yearly variation, it has to be periodic, it has to come back from where it started. Okay. They have to be periodic. And yeah, so this is starting from January, February, March and so on till December. Okay. So, you can see that it goes approximately about plus minus 15 minutes you have to adjust for this day length correction. Okay. So, overall we have obtained the time calculation we have seen, which connects between what the sun says or the sundial says to what the standard watch should say. So, what sundial says to what the standard watch should say, okay? And it incorporates where exactly you are depending on the standard time location, east or west, and also incorporates the day length variation, which is accounted for by the equation of time. Okay. So, one point I should tell you that for each country we have a standard time, because a whole country should follow the same time, right. But if the country is very spread out in east west direction, okay, then it will be very difficult if you use the same time. Then in some part the sun will rise at 10 o'clock in the morning, and in some part it will rise at 4 in the morning. So, it will be very difficult if the country is spread out in east west direction. Okay. So, and for any office or anything running smoothly, you have to fix a time. So, if the office time starts at 9 and if it is middle of the night or sun is not out yet, you cannot go to the office, right. So, that is why for very wide in the east west, north south it does not matter. If it is wide in the east west direction, wide countries, often they have more than one time zone. Like in US you have 4 time zones. So, the time in New York is not same as the time at Chicago, it varies. Okay. So, that is how they manage this problem, and in India also we are thinking of introducing more time zones, so that the sunny hours can be utilized much more effectively. Like in Guwahati and Bombay, the sun sets at much later time. In Bombay the sun sets later than Guwahati, right. So, in Guwahati you should start your office hour little early and end your office hour little early as well compared to Bombay. Okay. Then what we can gain is that we do not need to use that many electric lights, okay, if you shift your office hours accordingly, and that is why people are thinking of introducing more time zones to save electricity, and it will be very, and we are in the solar energy course, right. So, we can understand why why it is very much needed to save electricity and go renewable. Okay. So, here I stop for today, and in the next class we are going to talk about the role of atmosphere in solar radiation. Okay. Thank you so much for your attention.